Good morning, students. Myself, Dr.Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in the lecture series of MSc Final Physics. In the MSc Final Physics, I am dealing with the fifth paper, that is Condensed Matter Physics, and we were studying about superconductivity. In our previous lectures, we have discussed what are superconductors and the empirical criteria that which type of materials are superconductors. Superconductors are the materials which possesses infinite conductivity. That means zero resistivity. So it has been found that these materials are superconductors and they have superconductivity phenomena below a definite temperature termed as critical temperature. That means for T less than Tc, the materials exhibit a special phenomena, that means zero resistivity, and above Tc, these materials behave as normal materials. So students, today we will discuss an important phenomena about superconductivity, that is Meissner effect. What is Meissner effect? Here I am taking a superconducting material. Initially I am taking the material to have a temperature greater than Tc. That means what will be the state of the material? Since temperature is greater than critical temperature, so the material will be a normal material, and we are placing this material in a magnetic field, and the condition is that material is normal. So this is the situation. This is my material and T is greater than Tc. This material is simply connected superconductor. Here I have shown a simply connected solid sphere superconductor. And this material, because of temperature, is in the normal state. And this is the external magnetic field. By placing it in the external magnetic field, the field lines are penetrating interior as well as the exterior of the specimen. This is the situation which is arised in the normal state. Now I am changing the situation. What I am doing, I am cooling the material so that temperature is below Tc. What change occur? As the temperature is less than Tc, my material will now be a superconductor because temperature is less than Tc. What is the change in the phenomena? Now, it has been observed that magnetic lines, they are only in the outer region. That means they are excluded from the interior of the specimen. This is very interesting phenomena, and this phenomena of exclusion of magnetic field from the interior is termed as Meissner effect. That means inside the superconductor we have B to be 0. So this phenomena in which B is 0 inside the superconductor, this phenomena is termed as Meissner effect. The reason behind this is we can say that superconductor has a property of producing magnetic mirror surface. Why I am saying so? Magnetic mirror. What we have done, we have placed a superconductor in magnetic field. By placing this superconductor in a magnetic field, it has been found that on the surface, a magnetic field is generated and the direction of the generated magnetic field is opposite to the direction of applied magnetic field. This is in accordance with the Lenz law, so that we can say when a superconductor is placed in magnetic field, then circular currents of large magnitude are developed inside the specimen, and these current loops, they exactly cancels the external applied magnetic field. Hence, inside the superconductor, magnetic field B is 0. That means flux cannot penetrate in the sample of a superconductor. So we can compare it with the phenomena of electricity. We have seen that if we have a good conductor, and we know that a good conductor expels static electric field by moving charges to its surface, because the surface charges, they develop an electric field which cancels the external applied field. Just as in a superconductor, we have seen that external magnetic field is repelled so that it cannot penetrate inside the superconductor. But here we have seen an example of simply connected superconductor, that is of a solid sphere. Now we can see if we are taking a multiply connected superconductor. What is multiply connected? Multiply connected means we are taking a ring which has a hole in it. Then it is observed that if we place such type of superconductor in magnetic field, then the phenomena is entirely different. Here I am showing the phenomena. Initially, here T is greater than Tc. That means the state of the material will be normal. And this is my sample, which is in the form of a ring. Since the sample is in the normal state because of temperature, so on application of magnetic field, we will see that field lines will pass in the interior as well as in the external region around the superconductor. Now, what I am changing? Now I am reducing the temperature. That means I am changing the temperature from T greater than Tc to T less than Tc, so that the nature of material changes from normal to a superconducting state. As the material nature changes from normal to superconducting, it is found that field line behavior also changes. What happens now? If we cool it below Tc, then field lines, they disappear from corner. Initially they were here, but now we can see that they have disappeared from the corners of the ring. This is the second situation we are further changing the situation, not by changing the temperature. T is still less than Tc. That means material is in superconducting state. We are withdrawing the magnetic field. Initially, we have applied in the first two situations. Now we are taking a situation in which H is 0. Then we can see in this third situation that induced current is trapped in the superconducting ring. Hence, we can say that a current which is termed as persistent current has been generated in the superconducting ring. So this is a very important phenomena of superconductivity. Now we will show that because of this Meissner effect, superconductors are perfect diamagnetic material. We know that relation between magnetic induction and magnetization is B is equal to HA plus 4 pi m. Here B is the magnetic induction, HA is the strength of magnetic field, and M is the magnetization. But we have shown from the Meissner effect that B will be 0. So substituting B to be 0, I get my ratio M by HA to be equal to minus 1 upon 4 pi. And we are well familiar that the ratio M upon H, this ratio is termed as magnetic susceptibility. That means the magnetic susceptibility for superconductors is less than 1, it is negative. Less than 0, it is negative. And what does negative susceptibility indicate? Negative susceptibility indicate that these materials behave as diamagnetic materials. Hence, superconductors material behave as diamagnetic behavior. But perfect diamagnetism and zero resistivity, these are two independent properties of superconducting state. Here, in order to derive the perfect diamagnetism nature, what we have used? We have used B to be 0. Here, we have not used rho to be 0. Rho is the resistivity. As for superconductors, resistivity is 0. So now we will show that diamagnetism and zero resistivity, these two factors are important factors for superconductors, but they are independent properties exhibited by superconducting state. We'll show these through Maxwell equation. And Meissner effect, they contradict the Maxwell equation. From the Ohm's law of electricity, we have current density J equal to rho E. It can be expressed as E equal to rho J. Here E is the strength of electric field, rho is electrical conductivity, rho is electrical resistivity, J is current density. And since we know that for a superconductor, we have rho to be 0. Resistivity is 0. So as J is finite, this is possible from the expression that E will be equal to 0. Now I am using the Maxwell electromagnetic field equation, which is curl of E equal to minus del B by del T. From Ohm's law, we have E to be 0. So putting the value of E 0, we get del B by del T to be 0. Integrating it, I obtained B to be equal to constant. But as we have derived that B should be 0 in accordance with the Meissner effect. But here, what we have shown? We have shown that B is constant and this constant is not necessarily 0. So, rho is 0 here. So, we can say that the condition of rho to be 0 and B equal to 0, these are two important and different characteristics, independent characteristic properties of a superconductor. B to be 0 is a special property, and this strong repulsion of external magnetic field is called levitation effect. So we can say that superconductors are the materials which have extraordinary electrical and mechanical properties because of the two important characteristic features. First is the E equal to 0. Here, for E to be 0, we have used electrical resistivity to be 0. So E equal to 0 arises from absence of resistivity. That means infinite conductivity, perfect conductivity. That means there is a no power loss. Hence, making a superconductor a very powerful material. The another feature we have derived from Meissner effect is that B is 0. And using B to be 0, here we have used B to be 0 and we have shown that susceptibility is negative. That means materials are diamagnetic in nature. So from B equal to 0, we have concluded perfect diamagnetism in superconductors, which leads to strong repulsion in the magnetic field. So in our today's lecture, we have discussed an important phenomena, Meissner effect, which states that inside the superconductor, there is no penetration of magnetic field. That means B will be 0. B equal to 0. In our next lecture, we will discuss about the type first and type second superconductors. Thank you, students, for watching.